Hi, everybody. Thank you, Jack, for that introduction. So changing gears a little bit, we're going to go from vertebrate diseases onto plant diseases. And I understand that as a plant pathologist, I understand what plant disease is, and it's kind of obvious to me. But since I'm not full of a room of plant pathologists, in fact, there are about like 7 of us, I'm just going to first start out with what plant disease is and what it looks like, because it can look like a lot of different things. So what is plant disease? So the American Phytopathological Society defines plant disease as the abnormal functioning of an organism. But at Ohio State, as practicing plant pathologists, we also like to add a little addendum to this, which is that this progresses over time. And this is actually really important because it distinguishes disease from injury, which is one of the first things that I really want to solidify in your guys' brains. So what does this look like? So we know that plants are very diverse, and diseases within plants make that even more diverse, and they can look like a lot of different things. So I have a few examples here to start us off. So one example, this is powdery mildew on poinsettia. So we can see, there is a clicker here, I was told. Can everyone see this clicker? This pointer thing?
Yes.
Awesome. So basically what we're seeing here is white fungal growth on the leaves of the poinsettia. And so this is an example of a plant disease. It's called a foliar disease. And so this will actually start out as one tiny microscopic spore that we can't see. And then this will start into maybe like a yellow spot, and this is like a chlorotic spot. That's what we call it, it's terminology. And then it'll grow, and it'll progress over time, and it'll get worse. And eventually, it will look like this sort of fluffy white growth on the leaf, right? So it's a disease that progresses over time, it gets worse. We've learned things. Okay, another example. So this is an example of what I think is a soil-borne pathogen. So I actually took this picture outside of my apartment in the summer. So I haven't diagnosed it because it takes a lot of resources. But I think this is a soil-borne disease because what we're seeing is sort of the progression. So take this scenario. So this dead bush over here, these are all the same bush, but this dead bush probably was infected first, and then it started progressing through these symptoms that we're seeing here, right? And then this bush probably started out looking like this. It's just kind of yellow, kind of sad looking, and then eventually it gets completely brown, right? Because what's happening is the roots are being infected. The roots are then not able to really perform their normal tasks. So what do roots do? Roots take up water, roots take nutrients from the soil, and if the root function is abnormal and impeded by this pathogen, then the roots aren't able to do that, and the bush just ends up looking, in a non-terminology sense, really sad, like this middle bush. And then it becomes dead, like the right bush. And so then as this pathogen that's in the soil starts to spread, it does that in a very logical sense, just like to the next closest bush, right? And then to the farther bush. So this is an example of a root-borne disease, right? Those, I guess, that's how I thought of it, at least, so we're not sure. But that could be an example. And then my third example is a tree canker. So I have a friend in the audience. I asked him, I was like, what's a really good way to describe what a tree canker is? And I think I asked you in the lunchroom yesterday, it's Somya. And he said that you can describe it kind of as a zombie apocalypse, in that the pathogen are the zombies, right? And they're trying to attack this tree. And then the tree's like, oh no, I need to sort of protect myself from this zombie apocalypse. So it creates this sort of border where it's throwing all of its defenses at these zombies to protect itself. But the zombies aren't really warded off by these defenses because they just want to eat brains. So this is sort of a war zone that we're looking at. And this fight can just keep going on, and the zombies are fighting and the trees fighting back, or the people, whatever. Anyway, so this is what we're seeing here. So these are all examples of diseases, right? But they all look really different. So it might even help in understanding disease to also understand what is not disease, okay? And I kind of mentioned this a little bit earlier. So some examples of things that might look like disease to someone but are technically not disease include insect damage. So when insects eat through a leaf, and mechanical wounds, like when a lumberjack hacks at a tree, but maybe he left after he did this and he didn't actually cut down the whole tree, theoretically. So these are actually what we refer to as injury, and the difference here is that injury is the damage caused by a transitory interaction, meaning that it's temporary. So the bug will come, the bug will bite the leaf, and then the bug will leave. Or the lumberjack will come, hack what he did, and then he'll leave. But that wound by itself will not continue to get worse because it's an injury and not a disease. So the fungus will keep growing, but the lumberjack will leave. So that's the difference between disease and injury. So then if humans and insects aren't causing diseases, then what is? So in plant pathology, we usually work with organisms that could be considered fungi, bacteria, viruses, and nematodes. So, and nematodes is sometimes in entomology, but here we consider it in plant pathology at Ohio State. So when I'm looking at these organisms, the first thing I want to specify about these is that these are all really small, in some cases microscopic, and in fact, the only time that you can see most of these is when they get to really high quantifications and like there are billions of like little bacteria there, and you might be like, oh, there's like some ooze there. That's a lot. But most of the time, these are really small. And these organisms are spreading through countries. They're spreading from countries to other countries. They're getting around. And I'm not really seeing any legs. I don't really see any wings. I might see some sort of like snake-like, kind of functionality here, but how are these tiny organisms getting around? And that's like a really important thing in plant pathology, is studying how that happens. So there are several ways that this happens. So one of them is water splash, water, and also runoff. So runoff can spread soil-borne pathogens a lot. And you can see in this photo that all these spores, I don't know if you can see it, I can see it because I'm like really close, but all these spores are being spread through this raindrop. They're just splashing everywhere. Another example is wind. So wind is a really good dispersal mechanism. But none of these examples are living, so these are what we call passive transmission. On the other hand, we can have pests, like whiteflies, and we can have pollinators. And these are actually what we refer to as vectors, which is what I'll be talking about today, because it's disease and vector biology. So that's kind of a broad example. So what is a vector? And actually someone asked me this when I came in, so I'm like, yes, validation, because I'm going to talk about it. So a vector is a living organism able to carry and transmit a pathogen and disseminate disease. So if you read this and you're like me, you might be thinking to yourself, but what about this guy from Despicable Me who said that he was a vector because he had both direction and magnitude? So given our definition by the American Phytopathological Society, is this guy a plant pathogenic vector? Does anyone want to say yes or no? Not you. I already showed you his presentation, but anyone else? No? Why? He's not a he doesn't agree with the definition. He's not a vector because he doesn't agree with the definition. Okay. So he could potentially not be. That is correct. But the definition that we have here says that a living organism. So let's start with that. Let's start with the first part of the definition. A living organism. We have vector here with his little flight cape. So let's do hypothetical situations here. So let's say that vector, since he is a bad guy to begin with, so he can have bad habits, he gets into smoking. So what vector doesn't know is that the tobacco within cigarettes can actually contain tiny viral particles of tobacco mosaic virus, which are highly resistant to heat, desiccation, and can actually survive a very long time and remain viable without a living host. So vector doesn't know this, but vector's flying around and smoking, and vector gets tired, and vector decides that he wants to land and take a little break. And he flies over this tobacco field and says, hey, I can go make my own and go take some of these leaves. So he lands in the field, and unknowingly, he will be disseminating the viral particles that could potentially, maybe not, but they could potentially be in this cigarette. It has been shown that that can happen. And then he then becomes a plant pathogenic vector in this scenario. Yay, it happened. Okay. Congratulations, Vector, he completed his life purpose. Okay, so changing gears a little bit. Who here knew that 2020 was declared by the United Nations as the International Year of Plant Health? Yeah, the plant pathologists. Great, but now you guys know that too. Okay, so it was 2020 is the International Year of Plant Health, and it's a really big deal for us as plant pathologists, as horticulturalists, and things like that. So in honor of this, I figured we would all be doctors for the day and be McDreamies for plants. And look at some case studies, okay? So we have 2 case studies that we're going to look at, and these case studies talk about plant pathogens that are vectored by insects. So we're all doctors, keep this in mind, and we're looking at our first patient, okay? So our first patient is an elm tree. So I'm going to circle some things, and then you guys tell me what, as doctors, you think is happening here. So we see this. Yeah.
Soil compaction.
So, okay. So as plant pathologists, we sort of look at the symptoms first. So we don't try and define what the symptom is caused by. So if I was looking at this, I'll give the first example. So I'm looking at this and I say, that side looks more dead than the other side. That's really as simple as we get. So that side looks more dead, and we actually call that dieback. Okay? So step 1, yeah. So the next one, we're going to take a little bit of a closer look at these leaves, okay? So anyone want to, yeah?
Chlorosis.
Yeah, we see chlorosis. That's actually what I had. So chlorosis is yellowing of the leaves. So great. There's one other thing that I saw, and I don't know if anyone will get it, so I'm not going to try because these are already predetermined in my PowerPoint. It's unfortunate. But so I also saw that there kind of are fewer leaves on these than the other parts of the tree. So that's kind of early defoliation. So the leaves are falling off a little bit sooner. Okay? And then the last thing is maybe if this tree was already pretty diseased and dying before the winter months, if we peeled back this bark, we might see these things that are called brood galleries. Okay? And these are actually created by, the elm bark beetle. Okay? So all of these symptoms together wouldn't technically give us a diagnosis because we would have to isolate the pathogen, but we're going to pretend that we can diagnose it from these symptoms. And we found out that this is actually Dutch elm disease. Okay? So, hashtag dead. Okay. I thought it was funny. So how does this disease kind of work? Like, what does this life cycle look like? So Dutch elm disease actually was introduced to the United States in 1920 because a furniture maker wanted to make furniture with elm from Europe, and they brought it over, didn't check it for anything, and it had Ophiostoma ulmi in it, which is a fungal pathogen that's able to cause diseases in elm trees. And it started spreading, and some of the elms were able to survive. But then later, also, the person who discovered, the scientist that discovered that this actually is how Dutch elm disease was introduced into the United States was a Dutch scientist, which is why it's Dutch elm disease. So she got credit for that. And then a few years later, another pathogen was introduced that was also in the Ophiostoma family, and it was actually a lot more virulent than the original, and that's Ophiostoma novo ulmi, which is why I'm using that one here. So how this works is we have a diseased tree, and the tree overwinters, and it was infected in the previous season, right? So originally there was a elm bark beetle in it, and the elm bark beetle made this initial line, and it ate through the tree. So when it did that, it laid eggs, okay? And these eggs in the springtime will hatch And the little hatchlings will actually carve through the tree at these angles that originally start as 90 degrees to the original place that they were laid, which is why these brood galleries look the way that they do. So it was the original mother carving through, and then the eggs carving from there. And so, cool, right? Now, I learned that this morning. So, so the way that these beetles are able to transmit the disease is if this was a dead or dying tree from this fungal pathogen, what will happen is that the fungus will start growing these reproductive structures in these brood galleries. These are synema, as we call them, or as you can call them, tiny fungus trees. So they grow kind of out into the brood galleries and they form these really sticky spores, asexual spores, on the top of the fungus trees. And as the beetle crawls through the little galleries, it'll get stuck with all of these sticky fungal spores on the back of the beetle. And then when the beetle flies and goes and starts eating through other trees, it will infect those trees. And that's how this is spread through the Dutch elm bark beetle. There we go. Not Dutch. He's not Dutch. Yeah, that's one of the ways this is spread. This is also spread through tree roots, but this is a really major player in the spread of this disease. So we finished our first case as McDreamy doctors. So that is Dutch elm disease, and that's how it's spread by the elm bark beetle. Okay, case 2. So we have tomato plants that I got off of Google, courtesy of University of Florida. This is a really great picture of this disease, so I'm really glad that they had it on there. So the first thing that we see as plant pathologists is what? Stunting. I love it. Okay, yes, we see stunting, okay, because the plant is smaller than the other plants. So the growth is stunted. Okay, so let's again take a closer look at the leaves. So what are we seeing?
Curling.
Okay, curling, yes, but that's the third thing that I have on this little slide. What else do we have? Anything else? Cupping, that is actually what I call the curling, yeah. Okay, chlorosis, yes. We see, well, you're trying to read this, aren't you? Or no? Okay, you actually knew, good. So we see chlorosis. And another thing you might not be able to see in this picture because I covered up the other tomato plants was that these leaves that we have on this other plant are smaller than the leaves on the plants that are healthy, that are next to it. And then we also have the cupping, okay? So these are all symptoms of what could be a viral infection, okay? But for viruses, we can't really see them using a microscope. We don't really have a lot of things to do as far as like looking and testing and plating. So we have to test in other ways. So if anyone has used a test that looks like this, maybe like, we often use the example of pregnancy tests because it works in the very same way, but this is a positive indication. So what we do is we think that this might be a certain virus, and then we use an immunostrip, that's what this is called, and we test for it. And so this is positive. And I'm just going to tell you that the thing that we tested for was tomato yellow leaf curl virus. So basically that's what this is. Yeah, this isn't as fun as #dead, but I had to use the same theme because I'm OCD. So, okay, tomato yellow leaf curl virus. So how does this sort of incorporate into the theme of like insect vectors and things? Because we didn't see any insects, Isabel. So basically, if you went into these leaves and you flipped one over, something that you might see is this. So these are whiteflies. They are major pests, especially in greenhouses. I've worked with tomatoes in greenhouses, and these things suck a lot. So basically, how these work is that they will feed on phloem sap. And this is a really great image that I found from a paper published by Daumier in 2000. Whew. Anyway, not there yet. And it's about barley yellow dwarf virus, but it's a really great picture of how this kind of works. So the whiteflies feed off of what we call phloem sap. And basically the phloem is just how plants transport their sugars and everything. So the whitefly's like, that's awesome. Free sugar. I want that. So it sticks its little nose. I don't know as many bug terminology as the last speaker. She did a really great job, but I'm a plant pathologist, so it's the nose. It sticks its little nose into the phloem and starts taking up all these sugars, and with it, it takes up viral particles, because this is how the virus is transmitted through the plant. And so the virus will go, and it will eventually diffuse into the midgut of the insect. And for tomato yellow leaf curl virus, it's actually been shown that for some reason the virus has been shown to be able to replicate in this area. And so eventually the virus will then, from the midgut, diffuse into the salivary gland. And much like the ticks that were just mentioned, when the whitefly feeds, it's also spitting into the plant, okay? And once the viral particles make its way into the salivary gland, that spit can also contain viral particles. So that's how this disease is transmitted, by whiteflies. And it is a really, really big problem, especially in greenhouses, but also outdoor. So, great job, guys. This is our second case closed, and we only had 2, so you're at 100%. Okay, so with that, I just wanted to take this opportunity because I don't get to talk about insects a whole lot, and I have a lot of insects on my crops that I work with. I work in ornamental diseases of winterberry, and I see a lot of insects that I take really great pictures of, so here they are. And these aren't actually insect vectors, but they're really great, and this is the end of my talk, so I wanted to show them off. So if anyone has any questions, I can answer those.